So first of all, I'd like to thank the organizers for having such a wonderful conference and in such a beautiful city, and also for inviting me to give a talk. So I'm going to talk about let's go back here. So I'm going to give a talk about a work, joint work with Hayashi, Jefferson, Kim, and Omori. I believe Omori and Jefferson are here. And Jefferson is my student who's graduating this year. He's very good. So I'm going to talk about Calabi Yau singularities and superconformal field theories, some aspects of them. And it turns out that what is relevant for my talk is that singularities of non-compact Calabi Yau threefold get related to conformal theories. And this happens in two different ways. If you consider elliptic Calabi Yau threefolds, this class gets related to six-dimensional superconformal field theories with 1,0 supersymmetry in the context of the F-theory compactification. So this is one class of conformal theories, that's in 6 dimensions. And more generally, if you consider Calabi Yau threefold singularities, where some 4 cycles shrink in the context of M-theory, this corresponds to 5-dimensional superconformal field theories with n equals to 1 supersymmetry. So physicists, string theorists in the past few years, past decades, have been very interested in these higher dimensional conformal field theories, and we have studied these for both understanding classification of these theories and connecting geometrical aspects to aspects that we learn about conformal field theories from. So it's natural to believe that they will have some role in topological aspects of string theory, and that's an aspect that I would like to emphasize for the talk today. So in particular, so the quantities of interest that we would like to understand in these contexts, in the context of a string math conference, will be topological strings, in particular for Calabi Yau threefolds. And since the Calabi Yau threefolds are related to conformal theories, you may want to connect these two facts together. So, studying the conformal topological string amplitudes, there has been some progress in the context of compact, in the context of non-compact Calabi Yau. We know the full answer, at least for the cases of the toric ones and some generalizations thereof. So I would say, in some sense, the non-compact Calabi Yau case is quote-unquote solved, in the sense that the answers we know how to compute. We heard a very nice talk from Jörg yesterday about some aspects of that, and the last talk we heard from Ed was also related, can be mapped to a situation involving non-compact Calabi Yau, which gets related to the matrix integrals and so on. So that's a class where we can really understand things, compute things to all genus and so forth. The case which has not been as much progress is in the context of compact Calabi Yau manifolds. And in that context, things are much more complicated. So this goes back originally to the computations that we started. This is again 25 years ago in the paper with Vershatsky, Cecotti, and Oguri. We managed to compute amplitudes all the way up to genus 2. Genus 0 was already done. Genus 1 and genus 2 is what we added. And we came up with a method to try to study some aspects of these theories. Basically, what we found was that the partition function of compact Calabi Yau topological string, which morally should be holomorphic, is not quite holomorphic. But we found what's that anomaly. So getting rid of that means that we can understand its holomorphic pieces. And therefore, all we had to do, since the moduli space of Calabi Yau was compact, since it was morally holomorphic, all we had to give is the order of its poles and the structure near poles or subleading powers of poles. So with a few data, which is the boundary data near the boundaries of moduli space, for each genus, we could control the amplitude. So in other words, the amplitude could be reduced to finite data and computed. But you had to do some finite computations for each genus, some computation which grows linearly with G. If you do some of those computations, we could do all amplitudes for that particular genus. And so we managed to do the genus 2 case, but using similar techniques, Clem, I think, extended to genus 51, if I remember my numbers correctly. But anyhow, you can go up to high genus, but not infinite. You cannot go all genus. So compact Calabi Yau is difficult in understanding topological string, and it's one of the major open issues in the topological strings 20-some years or 30-some years after the definition of topological string. Okay, but there's also another reason to study topological strings on compact Calabi Yau. They are partition functions of black holes in 5 dimensions. So as physicists, we are interested in gravity theory and black holes in particular, and we want to count how many there are of various charges. And in the context of compactification of M theory on Calabi Yau threefolds, there are one-to-one correspondence between the partition functions of topological strings and the partition functions of spinning black holes. So that's why physicists would be interested, even if they are not interested in topological aspects of string theory. So I want to first briefly review the connection with black holes. So let's start with the original kind of simple black holes that we studied back in the mid-90s, beginning with the work with Strominger. So the black holes we studied involved studying type 2B on T4 times S1, or K3 times S1, or the dual description, which is in the M theory language, T6, or K3 cross T2. So this is a kind of a, you could say, a boring Calabi Yau, T6, or K3 cross T2. Not a general Calabi Yau threefold, but a special one. So in these contexts, it turns out that you can follow the dualities and find the following configurations. So first, you study type 2B with D3 branes wrapped around a 2-cycle in K3 times S1. In other words, you take a Riemann surface inside K3, you multiply by a circle, that's a 3-dimensional object. You wrap a D3 brane around this, and that turns out to be the object we want to study. And in the context of M theory, this turns out to be related to the M2 branes bound around the same geometry. More precisely, the map would be something, they're dual to one another. And in particular, if you take a genus G curve inside K3, the moduli space of how many ways we can wrap the M2 branes around the genus G turns out to be related to the symmetric product of K3 G times an extra R4. So the connection between them is the following. If you take K3 times S1 and take a Riemann surface inside K3 and wrap it also around the S1, and in addition, introduce n units of momentum around the circle, this corresponds in the M theory language to considering the bound state, a bound state of M2 branes involving n classes of this T2 bound to the same Riemann surface inside K3. So this is again a 2-cycle class inside K3 cross T2. Counting this turns out to be related to counting D3 branes wrapped around this geometry with an extra momentum n. So perhaps I should add one word here. From the viewpoint on the left-hand side, this also shows that this computation has something to do with the strings in the following sense. If you take a D3 brane and wrap it around the Riemann surface, you get a one-dimensional object left. 3 minus 2 is 1. So you have a one-dimensional string, and you can put a momentum n around it. And what that means is that if you compute the elliptic genus of that string, which is the momentum around that circle, that's computing for you the partition function in the language of Calabi Yau of the same Riemann surface bound to n tori attached to it in some form, and the moduli space of that. So the computation of topological string in this context gets related to elliptic genus in this other side of a string. And the holographic statement of this is that if you take ADS3 times S3 times K3, this is the near horizon geometry limit of a string wrapped around where this detail of this depends on which Riemann surface we pick inside K3. This is holographic dual to the G-fold symmetric product of K3 if the genus of that curve is a G. And the corresponding string enjoys 4,4 supersymmetry, and there's SO4 symmetry, which is SU to left times SU to right rotation, and these directly relate to the SU2 and SU2 left and SU2R symmetries of the 4,4 theory. Anyhow, the details of this is not that crucial here. You can compute the entropy of this, the growth of these black holes, and the entropy goes like the central charge of the string, the left moving degree of freedom, which goes like 6g plus 6, where g is a genus, times n, which is that momentum around the circle, and that gives you the agreement with the Bekenstein-Hawking entropy for large n and g. Okay. And so the spinning part, you can also introduce the spinning part of the black hole, and the SU2 left captures the spinning aspect of the black hole. Okay. So now, what do we want to do in more general is that we want to replace the K3 cross T2 with a Calabi Yau threefold to get in the context of the M-theory description. This is the more general setup. And again, we can route M2 branes. Now we want to compute M2 branes wrapped around 2 cycles in the Calabi Yau. And again, the partition function of these are captured by topological string amplitudes, and we do not know how to compute them. So we are kind of stuck there. And then for general Calabi Yau, there is no strength. However, if there's an extra T2, in other words, if the Calabi Yau is elliptic, roughly speaking, you have elliptic fibration over a 4-dimensional base, then the F-theory description, if you take F-theory on this geometry, you go down the 6th dimension on a B4, and then you go down 1 more dimension by adding an extra circle, and the duality between F-theory and M-theory says that if you go down to 5 dimension in this way, in type 2B language, in M-theory you go compactification of the elliptic threefold. So the topological strings on elliptic threefold gets related to this F-theory on this background times the circle. And again, you can do the same as we did before. You can wrap D3 branes around this Riemann surface inside B4 times S1, and you put a momentum n, and it turns out that this is the same as the class given by a Riemann surface inside the base of the F-theory, glued to a class which is n times the T2 in some form. So then what we learn is that the elliptic genus of these strings, in this case, now computes the Calabi Yau threefold. So in other words, without doing any computation, just from the structure, we learned that the topological string amplitudes for elliptic Calabi Yau threefolds is the elliptic genus of a, in this case it turns out, a 0,4 string. This is just an equivalent statement following from string dualities. And you can actually compute, this was discussed briefly in my paper in 1997, so there's a C left and C right, you can compute, and you learn some aspects of the growth of the topological string, and so forth. So this is the duality. The holography will be extended now in this context to AD is 3 times S 3 times the base of F-theory. So this is extended, extends the holography to a new class, but now the dual conformal theory will be some conformal theory instead of with 4,4 with a 0,4 supersymmetry. And again, the elliptic genus is the topological string partition function, is the black hole partition function. So these 3 aspects come together in this context. Okay, so how can we compute, how can we come up with what this 0,4 2D conformal theory is? Well, we don't quite know. We know abstractly it should exist, but how do we actually concretely study it? So in some examples, if you study 1,060 superconformal theories, the corresponding strings turn out to be, of course, the same strings we're talking about with 0,4, but for them, for some examples, we have a quiver description. So we may be able to somehow stitch together these degrees of freedom, somehow to come up with a description of the strings in the compact case as well. At least that's a goal. So let's start with a class of elliptic models and see whether we can get some mileage from this. Let's take the Calabi Yau threefolds of the form T2 times C, modeled out by some Zn times Zm, where the Zn and Zm generators are like this, where you have the, depending on which circles they act, you have some kind of action like this. You have different directions you can act, or you can make it to be alpha and alpha inverse, and beta inverse are different bases you can write. But anyhow, so when you model out by these Z2 times Z2, Zn times Zm symmetries, not all N and M are allowed. The only ones which are allowed are the ones which are symmetries of the torus. And so in this case, you will get some conformal theories if if you view these as F theory on the corresponding elliptic threefold, where you view the T2 as the elliptic fiber, so you get some conformal theories, and you get singularities over the locus of these fixed points. So you have singularities of locus of these 7 branes, where you have these fixed points. And this was actually originally studied by, in the physics by Vershatsky and Johansson, where they call these colliding singularities. So you have, depending on what singularities you have, you get a different conformal theory. So here I've just listed what is known about what kind of symmetries you mod out by and what kind of conformal theories you get. These are, what this notation means here is that you get a singularity that you can blow up in the base of the F theory. And here the number of circles denotes the number of P1s you blow up. And the integer there denotes the normal bundle, the degree of the line bundle in the language of with an extra minus sign of the geometry of this normal geometry to this P1. So this geometry of this one, for example, is the O minus 1 bundle on top of P1, and similarly for all the other numbers. So you get some collection of these theories which people have studied, and we understand these local story relatively well in terms of the resolution and the conformal theories they give rise to in 6 dimensions. Okay, so there's a list. As you can see, each one of them will have some global symmetries at the left and the right, and that basically means these 7 branes which carry gauge symmetry in 8 dimension behave like global symmetries at the level of the corresponding conformal theory. So, for example, here you get an SO8 times SO8 global symmetry. Here you get E6 times E6 global symmetry, etc. And these are the endpoints. So these are kind of like a generalized quiver type theories. Okay, so this was a non-compact case. If you want to go to the compact case, well, you just take C and C and make it compact with some Zn times Zm, and you try to then see what's the geometry of this theory. So if you take, for example, Z2 times Z2, you get, in the C2 part, you now get, instead of 1 fixed point, you have 16 fixed points, because now you have replaced C2 by T2 times T2. And each one of them is that O minus 1 theory I was telling you about. And each one of them has an SO8 global symmetry. Namely, there's a 7 brane going this way and that way. But now, the difference is that the SO8 global symmetry, which is on the 7 brane, since it's in a compact geometry, it gets gauged. So the global symmetry of the conformal theory now gets gauged. And in fact, it stitches together a bunch of them. So the geometry of how they get gauged is exactly which tori have common, which fixed points. And so from that, you get the geometry, and each one of them, where you gauge it, corresponds to an extra O minus 4 over P1 geometry, because it's T2 mod Z2. And so you get a geometry of interconnection of these P1s and their gauging in this form, where each 4 here corresponds to the corresponding SO8 that you're gauging in the vertical or horizontal direction. And so, and then these are the ones that you had before. So each 4 of them gets gauged by one of these SO8s, vertical or horizontal. And so this gives you the interconnection of how you glue these conformal theories together to describe the full theory in terms of the matter content. So the first statement is that the matter content of this theory from the physics side, namely it's gravity coupled to some matter, this describes the matter part. The matter part of the theory is captured by these conformal theories in this way. You can check the gravity anomaly cancel, so you have all the degrees of freedom correctly, including all the multiplets and so forth. You can check that. So we seem to have a perfectly complete model as far as the anomalies and all that seems to be concerned. Looks good. One can also check that the 2-cycle lattice modular sum identification is self-dual, as it should. So this was just Z2 times Z2 example. You can do other example like Z3 times Z3. Again, you have now geometry like each one of them now, instead of just 1 node, you have 3 nodes. And moreover, on top of one of the nodes, there's an extra SU3 gauge symmetry. And the corresponding direction here becomes a T2 mod Z3, gives you an extra O minus 6 bundle over P1, which is, in this case, E6 gauge symmetry. And you can check again the anomalies cancel as they should. So you have all these bunch of theories depending on what you do. So if you have things which are more complicated, like Z2 times Z6 or Z6 times Z6, you just get a more interesting pattern of which gauge symmetries and you're gauging. Sometimes you get some outer automorphisms acting, making things like F4 and G2 showing up. So there's some interesting pattern. And in all these cases, you can check anomaly works. So we have the full matter content as expected for these theories. So now the question is, how do we describe the corresponding theory? So what do I mean by the corresponding theory? It's corresponding to D3 branes wrapped around 2 cycles. Can we describe the corresponding 0,4 theory in 2 dimensions for whose elliptic genus may give us the topological string amplitudes? So let's go back. So for the case of the Z2 times Z2 model, the local description of the quiver has been given in various papers, and so they look some kind of a quiver data like this, involving some gauge group involving SPN gauge theory and OK gauge theory. So there's some description and these NIK depends on the class of the cycle we are wrapping the D3 brane over. So how many N's and K's you choose will give you corresponding patterns with some matter content. Again, the detail is not that crucial for me. The main point I want to say is that there's some expectation of what quiver we should be getting in this case. And so we would get a holographic statement of the form that ADSU times S3 times, in this case T4 mod Z2 times Z2 is some kind of a quiver involving gauge groups with the products of OKs and SPs. Exactly which Ks and Ns you choose depends on which fluxes you put in this geometry. We can compute the anomalies of this quiver, and we can compute and we can show that the corresponding anomalies give you the central charges that you expect from the D3 brane wrapped around the cycle. So the C left and C right work, so you can have the first rudimentary check that it has a chance of being correct, that you get the right anomalies. And so one would ask whether the topological string partition function of that is the elliptic genus of this quiver, and whether that's the same as the partition function of this black hole. It would be interesting to check this, and the leading growth naively works because the central charge works, but there are some hints that they don't have there's some aspects of this that needs to be completed, it seems, because the symmetries are not quite matching. These quiver theories have extra symmetries that the gravity side doesn't have in particular. So it suggests that there is some ingredient, maybe some interactions with the quiver that has to be appended. So it seems to be, it's on the right track, but it's not clear it's exactly the right thing or not. You get some expressions like this that you can actually work and compute. Nobody has computed topological string amplitudes for these cases, so we didn't have any checks to do. And so I would like to now talk about the extension of this to the non-elliptic Calabi Yau threefold. So so this was good for M theory and elliptic threefolds, but what about non-elliptic threefolds? In that case, there's no string. And so, but now the idea is we want to use a similar idea of trying to get a singular Calabi Yau stitched together through the conformal theories, which have extra global symmetry that are somehow gauged. So basically the idea is that the compactification is equivalent to gauging global symmetries of pieces stitched together in some particular way. So that's the basic idea. So let's consider a 5D superconformal field theories in this context. And I want to talk about a specific example, even though this can be generalized. We want to look at the quintic threefold modeled out by Z5 cube. This is also known as the mirror quintic threefold. So this sounds like it's too complicated. Why do we start with the most complicated example? You might think quintic is a much simpler one. Why am I going to the mirror quintic, which has 101 moduli instead of just one moduli? It sounds like a crazy thing to do. Surprisingly, this turned out to be easier than quintic to discuss in this context. And the reason for that is that the mirror quintic has so much singularity, you can basically take this compact manifold and put it into pieces made of these singularities more easily. Whereas the quintic itself has no singularity, so there's nothing to piece together, kind of. So the theory is a bit harder to actually decompose to pieces. So this is actually easier to try to decompose to pieces. So let's start with that. So you have the quintic you mod out by Z5 cube, and it turns out that the Z5 cube theory when you multiply Z5 cubed, you get interesting superconformal field theories in 5 dimension at the fixed points of this action. In particular, for every triple of these coordinates, you get a superconformal theory in 5 dimension. And so therefore there are 5 choose 3, which means there are 10 superconformal field theories on this compact Calabi Yau. Moreover, for every pair of them being 0, the normal geometry corresponds to the geometry corresponds to an A4 singularity over a P1. So in other words, this is the usual statement that if you have a Z5 action, the M theory in that geometry will give you an SU5 gauge theory. So we expect an SU5 gauge theory for every such pair, and therefore that means that there are 10 SU5 gauge theories, and the locus of the SU5 singularity is a P1, so that gives you the corresponding gauge coupling constants. So this is actually nicely characterized in terms of this diagram. So we take this pentagon. For every triangle in this pentagon, you get a superconformal field theory. So these triangles here, it's hard to read them here, but for every triangle here, you get a superconformal theory. And for every edge of these triangles, you get a global symmetry. So in other words, each of these conformal theories have SU5 cubed symmetry. And each circle here, like for example the 1, 2 circle, will gauge the symmetry of the 1, 2, 3, 1, 2, 4, and 1, 2, 5 superconformal field theories, which has the edge 1, 2 in common. So in other words, you pick a particular edge, and you fix all the triangle which has that common edge, and that means that you're gauging that symmetry. So this gives you a description, a complete description of the non-gravitational part of this quintic. So you can compute, just to make sure we count all the degrees of freedom correctly. So if you want to compute the H11 of the Calabi Yau, you remember there are 10 superconformal field theories for these triangles. You can show each one of them has 6 moduli. These are the local degrees of freedom of the superconformal field theory. And then you have SU5s, there are 10 SU5s, and each one of them has rank 4, because of the Cartan of SU5 is 4, so you get 4 times 10. And then there's one parameter overall, which is the moduli of the P1, which SU5 is wrapped around, and that gives you the last parameter, so it's a coupling constant of SU5. So all these parameters are accounted for in the gauge theory language. This one is the gauge coupling constant, which is common, which we have to take it to be common for the SU5s. This is the Cartans of SU5, and these are the local degrees of freedom of the superconformal field theories. So you get all these accounted for in the language of superconformal field theory. So now you want to compute this, and the first thing actually in this context is to remember is that there is the topological vertex turns out to be very useful in these computations for the local superconformal field theories. And for the local superconformal field theories, which I will call this the 1 plus vertex, gives you some description of how you get the answer if you just had the superconformal by itself. If you had just one of these superconformal field theories, we know how to compute them. There's also a mirror description of this topological vertex, which I call 1 minus, which was studied a while back. So the standard topological vertex, there's a formula for this in terms of shore functions. I won't bother saying it, but basically these are the diagrams for which, using rules similar to Feynman diagrams, you can compute the topological string amplitudes for the local geometry. And for the 1 minus vertex, which you can view as a mirrored geometry, there's similar computation that one can do. The answer is much simpler. It turns out the representations here of all 3 should be equal, and there's some factor here which is not too complicated that gives you the mirror answer for this case. This turns out to be, one way of thinking about this is in terms of a U1 gauging. So this is morally, you should think about as a U1 gauging over this path. And so now the main question here is, we know how to describe these local patches. These local patches is what we already understand. So these are the conformal theories I was talking about, which there are 10 of these guys. Then for each triangle, we get 10 of these guys. And you see that each one of them has these 5 parallel lines in this toric picture, which corresponds to SU5 cube symmetry of these theories. So we know how to compute these using the regular topological vertex, but now somehow we have to gauge every three of them into with one SU5 gauge symmetry. So how do we do this gauging? So it sounds like we should have a rule for this gauging vertex, like what we have for the 1 minus vertex for the SU5 gauging version. And in fact, following the work of Hayashi and Omori in the previous work they had done, one can extend the definition of gauging from the 1 minus vertex to something which looks like the SU5 gauging. So you can call this the N minus vertex. And what you can find, the formula for it, a proposed formula for it, which is a naive generalization of what they already did for the 1 minus vertex. So I won't bother describing the full detail about what is the motivation, but it's similar to what they had done in the previous work of theirs. So you can come up with this prediction. So then you put this vertex here for the SU5 gauging, and you have these local pieces of topological vertex put together. So you have some plus vertices and some minus vertices put together in this way, and you can try to compute it. So there are many parameters, but to simplify the discussion, let's take the sizes of the blowups of this local geometry to be the most symmetric direction by some parameter which I will call gamma. And let's take the gauge coupling constant parameter, the 1 over g squared, to be labeled by the Kähler parameter L, so that I have, instead of the 101 parameter moduli space, we just have a 2 parameter submoduli space of this problem given by gamma and L, so that we can do computations. So you can do the computation. For example, if you take L was this class here, which gets related to the underlying class of the quintic, mirror quintic. And this gamma are the local blow-up classes. So if you compute the different degrees of L and count what genus invariance you compute these numbers using this topological vertex readily and get this kind of formula. And if you can do the 2 parameter one involving L and gamma. So gamma was this, L was this one, so you can also do these computations for those. So for, let's say, gamma 0, 1, 2, and so for some low numbers, you do the computation, and you get this. Okay, so we are very happy. We have some numbers. Could these be correct? So we asked our good friends, Dave Morrison, who's our chair here today, and Sheldon Katz, to do this computation. And it was not a trivial computation by any means, but they kindly agreed to do the computation for us. And they found this answer, which disagrees with our answer. So you see their answers is not too different. It looks similar. In fact, the L equal to 0 ones does agree, and this is not that surprising. We have to get agreement for L equal to 0 because that's the local piece of the problem. So it better agree and does agree. But the L equals to 1 is kind of close, but not exactly right. So then we kind of go back and see what the issue might be. So the issue is actually what is the meaning of this SU5 gauging. And if you go back to geometry and try to understand the SU5 gauging, you come up with a picture which is kind of like the pencil surfaces of various kinds and with some blowups and so forth here, which gives you a different picture for the computation. So you can stitch this instead of what we were doing as SU5 gauging as pieces by hand and trying to improve your computation. And once you do that, you can get the naive answer corrected and you actually get the answers they gave. So you can actually refine the computation we did to get the answers they gave us, but the problem is we do not know a systematic way to do to all degrees. So the question is, can we actually continue the systematics of this to all degrees? And so far we do not know. However, the very fact that these local pictures seem to give you answers which we usually thought are global compact things shows that we are on the right track, that we are very close to some kind of a formalism which corrects our formula and gives you the correct answer. And I think it's very promising. And so in the 25th anniversary of BCOV paper, I was hoping we will report the final full answer, but we don't have it. But I still feel that we are very close to it now. Okay, thank you for reminding me. Hopefully we'll have a conference in 6 more months here. We'll come back, hopefully. But thanks for reminding me, so we'll have to work harder. So yes, this agrees with the computation that Sheldon and Dave did for us. So we have to find how to correct the SU5 gauging vertex to agree with the geometric picture. So that's the missing ingredient, the SU5 gauging. But from the physics, so this is the math side, but what is the interesting part from the physics? The physics is telling you this. You have 10 conformal theories, they're standalone objects, but you cannot just gauge them naively because that's not a good thing to do. In the following sense, it's not a good thing to do. It is not a conformal theory anymore. Is it, roughly speaking, in the 4D languages, as if you're doing the non-asymptotically free theory. It's like you're going beyond the asymptotically free bound. So you're taking a system which is good by itself, but now you're saying I'm gauging something which if you did in the usual theory, you would have said, wait a second, I have too much matter. It won't be conformal. But nevertheless, there's an answer here. Namely, we know the answer should exist because the picture we gave from the Calabi is correct. We know that there should be a way of gauging. But remember, there are pieces that are missing in the description of the gauge theory. For example, we had 10 SU5s, and naively you could have said that these 10 SU5s have different gauge coupling constants. If you did that, it would have no geometric analog. Only if these gauge couplings are equal, it corresponds to Mary quintic. So only for very special ways, you should be able to extend this and get an answer. And so somehow that ingredient, that's the magic of gravity making it work, which is the corresponding SU5, particular SU5, which is kind of a swampland condition that you cannot just do arbitrary gaugings of this, but very specific ones, is hitting us here too. So we will learn something about what does it mean for the full quantum system of matter to be able to couple to gravity. And so this would be a good toy model for understanding what are involved in getting the full gravity in this context, which is non-asymptotically free in this language in 5D system. So I don't know how much time I have. I think our chair has been very generous with me. Well, how much time? 15 minutes. Wow. Yes, our chair is very generous. But anyhow, so at any rate, I'm more or less finished. So we have seen that we can stitch local CFTs in 6 and 5 dimensions to have a complete direct description of the non-gravitational sector of some compact Calabi Yau threefold. And we can use these to propose some kind of dual descriptions which have ingredients which look right, but it cannot be exactly right. And we have some pieces which are missing, and the pieces that are missing seem to be, at least it's low degrees, which seem to be able to fix them, but we do not have a systematic way to do it for all degrees. And I think I will stop here. Thank you.